Hi, welcome back to the part for the embedded system, where we're gonna do the practice of the previous theory that we introduced in the part 3. And the code here, actually all of the important steps where we have to initialize or configure the AXI GPIO 0, there's no changing. So only changing how we using the GPIO and the name just a little bit, but everything was the same with the code that I introduced in the part 2 of the embedded system series. Now what we're trying to do is trying to demonstrate that we, as the C code, we're writing 32-bit data to the memory address range assigned to the AXI GPIO, and there will be a mechanism that only extracts the last 4 bits and stored in the corresponding GPIO register in the AXI GPIO, and those last 4 bits will impact on controlling the LEDs. So, for example, we have this function provided by the driver generated by the SDK when we export the hardware to the SDK. If we want to know about the detail, we can control and left click on the function, and here we will be guided to another file where they store the function, and this is where we need to see, and we control left click again, and we are here. If we want to understand some parameters, then we can scroll down, we can scroll up a little, because in above the command there will always be a very clear command description. What are the parameters and the function of the command? So how could I know that they will extract only the last 4 bits from the 32-bit and store it in the corresponding GPIO register? Here they say write a value to a GPIO register. Write a value to the GPIO register doesn't mean that we write directly from our C code to the GPIO register, but we write a value to the memory address range assigned by the maybe the Vivido for the GPIO register. And when we write to that memory address range assigned to the AXI GPIO, the software will automatically writing from the memory to the corresponding GPIO register. And the data that we write has the width of 32 bits. And they also say that the GPIO core, if implemented in smaller width, which is in our case, because we configured our GPIO width to be 4, and 4 is very small compared to 32 bits. So they say only the last significant data is written. Like how many bits are significant for the last of those 32 bits, of course, based on our configuration. We have a register GPIO of 4 bits, so the 4 last bits in the 32-bit will be the significant data and written into the corresponding GPIO register configured with the 4-bit width. And the 32-bit write is indicated by this function AXI GPIO out date 32. If we control and left click on the function again, we can choose whatever file that we want to see the definition of that function. In our case, it might not be important, so we can choose either. Maybe this one? Yes. So this is a defined, means this function is defined as here, and then we control, let's click again, then we click OK, and now we are guided to the whole thing of the function. And discussion of what they are doing is out of the scope. We just need to understand we just need to understand that this command will write a 32 bits to the memory address range assigned to the AXI GPIO, and there will be another supported mechanism which we don't see, will help us to extract the last 4 significant bits from the 32-bit and store it in the corresponding GPIO register. And then from that GPIO register, we will control the LEDs connected to the AXI GPIO. Okay, so now this is the data from, as we say again, we are playing the C code. So the data that we're writing is 32-bit to the memory. So we writing this data. We say this is the unsigned 32-bit data LED, and this is indicated in the form of the hexamal. And here we will write our data to the LEDs. Writing the data to the LEDs means writing to the AXI GPIO, the GPIO 0 that we have in our hardware design. The GPIO 0, the AXI GPIO that we created using the intellectual property in the programmable logic or the FPGA domain of our Zynq chip. And this is the values, 32 bits, that we write to the register, and the register that we're writing in this case will be the try register if we look back in the document. So the register that we need to use in order to, because this function will set the direction of our LEDs, and the register responsible for storing those configurable information is the GPIO try. And in order to determine which address starts from which address that we will have to store this data, we have to base on the address offset. And they say we can determine the real address of this GPIO try register represented in the memory by using the base address plus the offset. So even though that you see we have like only 4 numbers of hexamal values, and the base address, let's go back to Vivido, the base address has more than 4, but if we add this base address with this offset, if we add this base address to this offset, then the number 4 here will be corresponding to the last digit. So if we add them together, the value that we have will be I will write them down here, 4120,000 plus, sorry, I'm missing 10, plus another hexamal value which is 0004. So we need to understand that this is start from the least significant, so the value that we have will be 4. Okay, so another example, if we use this base address and we plus this offset 0, we plus that offset, the result is here. Okay, so start from this address, we will write, start from that address, we will write a 32-bit data starts from that address when we set the direction. Of course, as the purpose, we want to set our LEDs to be output, and to set the LEDs to be output, we need to set all of the LEDs to be 0. However, if we put it as 0, we cannot see any changing, because let's let's try to do the debug. For example, if we want to do the debug, we need to put some debug function before building the program. So we can double click on the line that we want to put the debug, and you will see there will be a circle gray putting on that line. And next, now we need to put on this function, which is the write to the memory address range, represented the GPIO data connected to our LEDs, and this is writing to the memory address range, which is assigned to our GPIO try register for configuring our LEDs as either output or input. Now, after we put the debug function, we need to press build, and then we can launch as like a normal running program, or we can launch as the debug function. In this case, we want to launch a debug function in order to demonstrate everything. And now we will be guided to the debug perspective. If we want to go back to our normal perspective, what can we do? We just need to click on here and we will go back to the coding perspective. But now we want to see the debug perspective. And as you can see, there will be a small memory window here where we can add the memory that we want to see. Okay, go back to the document. We can see that our GPIO data register will be presented by the base address plus this offset, and this offset is totally 0. So our base address plus this offset is the base address itself. We click OK. And after that, we need to choose the presenting value in those, let's say, in the memory address range. I would choose hexadecimal integer. Why do I choose hexadecimal integer? Because the one that I'm monitoring here is the register for configuration. Oh, sorry, the memory here that I'm monitoring is the register for the data that we're writing to the LED. I turn on which LED, I turn off which LED. However, the very first memory writing command will be into the GPIO try register. That's why we need to go back to the document. We see the offset and we plus with the base address. If we plus this one with the base address, then we will be in this one. It doesn't change much, it shows the same, because why? Here we can see we use some format presenting. How can we read this one? So this is the address, then in this range means the address 0 to the address. Okay, let's use Notepad to explain. So this is our base address. And then we have a range of 0 to 3. It means in this range we have the address in order as this is the first address, the second address, the third, and the final address in that range. That's what it means when you see a range here. But yeah, that's it. So if we write 32 bits into this, if we write 32 bits into this address, and the start address of that register is from 4, and 32 bits mean we need 4 addresses consecutively, and from 4 to 7 we have 4 addresses consecutively. So this value should be here, should be indicated here. Now let's change the value to something like FF, whatever, a random value. We save and we build it again. Now we can go back to the running perspective. We open the debug function and we run it as the debug. And yes, we have to choose it again. fail. If we fail, then maybe because the launching has not been finished. Now the launching is finished. We can click and we are here. Okay, now let's jump to here. We jump to where we have our first breakpoint. At the moment, this command is not executed by our processing system. That's why the memory address where we're gonna write to, no change. Now if we press continue to the next one, you can see the changing in this memory address. I don't know why it changed many others memory address, but in our case we just need to pay attention to this memory address range where we write our configuration data to the memory address range, which is corresponding to the GPIO try register here. You can see it here. I'm wondering why I'm writing to FF and here it appears to be only an F. So what happened if I write the F here and I build it again and I go back to the core perspective, I launch it again as the debug function. Yes, relaunch, and I change to the debug perspective. So now it's still in the launching process. When it jumps to that console with the blinking cursor, this is the indication of the launching process has been finished. Now we can look at our, we do it twice, so we can remove it by choosing the address and right click, remove memory from memory monitor, and then now we can try to choose the format value that it shows from the memory address. Choose hexadecimal integer. Now we again go here and we want to write this data and nothing changing. It means, as I say earlier, what do we have? From the C code, we'll write 32 bits to the memory, but only the last 4 bits will be stored in the GPIO register. So maybe the processing system already understands that that memory address range is connected to the GPIO register, which is configured with only 4-bit width. That's why it will constrain what we can write into this memory address range to be, corresponding to the GPIO register width. So it only stores the last 4 bits. It only stores the last significant bit according to our configuration in the width of the GPIO. So it cannot write another one. But for example, if we change the value of the F to 5, for example, and then we go back to the perspective and we will launch it again as the debug, waiting for the launching process finished. Okay, and we need to input this one. Oh, something wrong. Wait, if I close that memory window, we can open it again by going to Window, going to Show View, and choose. Oh, sorry, I chose the wrong one. Again, Window, Show View, and we choose Memory. Here again, shows too much. Right click and choose Remove. Right click and choose Remove. Now we will start. Now we haven't written this data into our memory, indicating in the memory address range. Now press it again. Yes, it writes the data to the memory range corresponding to the GPIO try, but it stores only the last 4 bits, as it knows that only the last 4 bits will be stored in the physical GPIO register. So when it writes to the memory, the processing system already made the constraint from this point already. So I think I made a mistake here when I say 32 bits, because from here, that is true that we write 32 bits, but the processing system, based on the configuration connected to it, it will constrain only storing the last 4 bits in the 32 bits in the memory address range corresponding to the physical GPIO register. So here it must be the same with like 4 bit. 4 bits. Oh, sorry, no. We have only, I think, 2 bits. So the 4 bits and the 4 bits here. Yeah, it should be like that. And that's where we see, that's where we see the action that we're writing to the memory's range representing the GPIO try register. But now, if we want to write the data to our LEDs, we need to write to the memory address range representing our GPIO data, and it will be in this cell. Because we're writing the LED data 32 bits, all 0 the same here, so we won't see any changing. So we can go back to the code perspective and change the value to, let's say, 1. Save it. And now let's see, as we have the last 4 bits is 5, so 5 in hexadecimal, 5 in hexadecimal will equal to how many in binary? We will see. So this is 4, this is 5. It means that the first LED is configured as input, the second is configured as output, the third is configured as input, and the fourth is configured as output. And we are writing the data to the, because the data that we're writing is 1 in hexadecimal. So in binary it will be 1. So we want to turn on, or it means we want to write the data 1 to the first LED. However, the first LED is configured as input. So whatever we write to an input is impossible, because if the LED is configured as input, it means we want to read the data from the LED instead of writing the data to the LED. And if we want to read the information from the LED, we cannot write the data to the LED. So with this kind of writing data to the LED, in order with the attempt to turn on the LED, the first LED, we won't be succeeded. Let's save and build it, and we will see the demonstration on the board. Oh. So I'm open the debug, and now I will just have to adjust a little bit in order to show the important thing. Now let's run the, we haven't launched it yet. Go back to the C coding perspective, launch it as debug. Yes. And now we need to wait for the launching process to start as we predict, because we config the first the first LED. I guess it should be, yeah, it should be this one. So this is the first LED, and we config our first LED to be, jump to the configuration. We config our first LED to be input. So if we write the data, see, the configuration is already configured. And now if we want to write the LED data to this memory cell in order to turn on the first LED, it won't be succeeded, as the first LED is configured as input. it cannot read the data that we output to the LED. It doesn't show, so it won't show any light up for that LED. And yes, even though that we already write the value, but nothing shows up here. However, I'm a little bit confused because our LED data should be 1, not 0. Why does it show 0 here? Save it. View it again. Oh, I think because we put the register as input, so even we cannot store that value that we want to write to the memory corresponding to the first LED, because the first LED is configured as input, so we cannot write to that first LED. So the processing system also understands the configuration. That's why we cannot even write to the memory express frame presenting the GPIO data for the first LED. Let's try another value. So the first LED is input. We cannot store that value into the memory range corresponding to the GPIO data. But the second LED is configured as output. So if we try to change the LED data for controlling the LED into the GPIO data memory presentation, it should be able to store here. So let's go back and then we modify the data. If we want to turn on this one, the second LED, then we will have the value in hexadecimal corresponding to 3. So now if we write to 3, Control S to save it, and then we build it again, and we launch it again as debug, and then we change to debug perspective. We need to wait for the launching process finished. Now it's finished, and we can choose the presentation of the value stored inside our memory address range presenting our AXI GPIO. Now we already changed our LED data to 3. We should be able to see that this value should be stored inside the memory. So let's try. Yes, now we need to run the configuration, the AXI GPIO. Okay, it's done. Now we haven't written any data yet. Let's write it. Yes, and it's stored 2. Why is 2 but not 3? Not write 2 but not 3 because it stored only this value. It stored the value corresponding to the second LED, because the second LED is configured as output. It might not be a little bit too clear for the LED, but the second LED now is on. Yes. And it doesn't store the first bit written to the first LED, because the first LED, the processing system understands that the first LED is already configured as input, so it doesn't let us to even write to the memory range representing the GPIO data of the first LED. So it should be 0. Now if we want to, let's say, write to the third LED, which also configured as 1, the value that we write to the memory address here should not be changed. If we write, let's say, 1 here, then we have 7. The binary value will be 7. Control save. When we control S, we already built it, so we just go back and then we launch it as debug. And wait for the launching process finished. We choose hexadecimal integer. Okay, now we will have a new data writing to the GPIO data register presented by this memory address range. And now nothing changing because nothing will be influenced. We would try to write the data that we just changed to the memory address range presenting the GPIO data register. As we predict that it will store only this one in the middle. So the value presented in this hexadecimal form is also 2, so there will be no changing in this value even though that we're writing new data to this memory address range. Let's run this command and we'll see. See, nothing changing, and our second let is still on because the one that we want to write to store in this memory address range is already configured as input. So we are not able and we are not allowed to store that value inside this memory address range presenting our GPIO data of the second let. Of the third let. Now if we wanna write the data to the fourth let, then we should be able to store that data because the fourth let, according to the configuration here, is an output. So if so, then we write here it should be 15. However, the data that we will be able to store inside the memory address range presenting our GPIO data presenting the 4 lets will only let us to store this one and this one, right? Yes. So the binary value presenting, let's say that the hexadecimal value corresponding to the binary value of 1010 will be 12. So we will see the changing in 12 here if we change it to 15. Even though we change it to 15, but because we're already constrained by the configuration data of our LEDs, so we have limited way to write to our memory here. To build, Control S to build, then we launch it again as the debug function. We wait for the process to be finished. Now it's finished. Okay. And the setting, nothing will be changed to this setting of this memory. This memory range representing the GPIO try data, the GPIO try register in the AXI GPIO, which corresponding to the configuration of our 4 LEDs. And next here we will start to write the new data to this address range in the memory presenting the GPIO data register, and because of the some constraint in the configuration, the value that we are able to store here will be different. We want to store 15, but for sure we will only see the 12 written to this. Oh, we see nothing. We see all 0. Why? Sorry, because 15 in hexadecimal doesn't make any sense. It should be F. So 15 in hexadecimal is F. My bad. So this one is F and This one should be, let me check. Should be C. I build it again. Sorry, 15 in decimal presented in hexadecimal is F, and 12 in decimal presented in hexadecimal is C. So that's why there's a error. This is an error. So let's go back to the C coding perspective and launch it against the debug function. And wait. So sorry for the mistake. X integer. X integer. Now, okay, nothing changing to the memory address presenting the configuration register, but now we will write the new data. Oh, we store the A. Oh, I think I made the math so wrong here. Oh, yes. So it's 8 plus 2, not 8 plus 4, 8 plus 2 is 10. So 10 in decimal presented in hexadecimal is A letter. Yep, so we write the A, not the F, because we are constrained. And that's the demonstration of between the theory that I demonstrate in the part 3 and what I'm doing here in the part 4, in order to make us understand what the data that we are writing, how many bits we are writing, and how many bits in them are actually stored in the memory of the processing system, and which part in the memory of the processing system presents our AXI GPIO block, and which address range memory presenting the physical register in the AXI GPIO. And thank you so much for watching. The video is really long, but I hope it's informative. Thank you so much for watching, and see you again.